Thank you to the organizers for the invitation to speak at this conference. And the goal of my talk is to present some progress on a program to derive particle physics from globally consistent F-theory compactifications with focus on deriving standard models. I will focus on by now well-known example of 10 to the 15 three-family standard models, which in addition have no chiral exotics and as a byproduct also coupling, gauge coupling unification. So the main goal of my talk is to actually present some new results that go beyond the chirality and gauge symmetry of these constructions, but also to determine the full-fledged charge spectrum of the theory, including charge matter vector pairs. In particular, the goal would be that with this information, we could find the domains of complex structure moduli where we would have the exact MSSM spectrum with no vector-like exotics and only one pair of Higgs doublets. This is the work in collaboration with Martin Bies, a postdoc at Penn, Ron Donaghy, mathematician at Math Department, Muyang Liu, my former student, soon to be postdoc at Uppsala, and Mariel Ong, who is a student of Ron Donaghy, and some other combinations of us five. There is also an earlier work on aspects of studies of vector pairs, also together with Ling Lin and Fabian Rühle. So, okay. So let me just highlight few key features of particle physics constructions in F-theory that presents globally consistent models by using toric techniques. So the starting point is construction of elliptically fibered Calabi-Yau fourfold, where the elliptic curve is chosen as examples of to be a hyperspace constrained in two-dimensional toric varieties, which are associated with 16 reflexive polytopes. So having this elliptic curve, we fiber it over three-dimensional base and impose Calabi-Yau constraints, where, of course, both coordinates of the two-dimensional reflexive polytopes and the coordinates of the hypersurface constraint are lifted to sections of specific line bundles of the three-dimensional base. For the toric constructions with the elliptic fibration, it turns out that this fibration depends only on the anti-canonical divisor of the base and two additional divisors that I'm referring as S7 and S9. Now, to obtain the chirality, we definitely have to put in flux. So this will be a flux that does not induce superpotential for moduli and sits in the vertical middle cohomology. And integrating this four-form flux over the matter surfaces determines the chirality of for particular matter representation. Last ingredient in this construction is that we have to ensure that D3 tadpole cancellations, the four-form flux induces the D3 brain tadpoles that are subject to this condition when that depends also on the Euler character of the Calabi-Yau fourfold. We have to ensure this condition in a way to have positive and integer value number of D3 brains. Furthermore, there is a non-trivial constraint on the integer value flux G4, where C2 is second Chern class of the Calabi-Yau fourfold. I'm having problems. Okay. So let's turn directly to the construction of the standard model. And this one turned out to be arise from elliptic fibration associated with a two-dimensional polytope F11. The actual space is P2 with 4 non-generic blowups and a hyperplane constraint that ensures this to be elliptic curve is of that form. Now, with this elliptic curve, we go on and construct the Calabi-Yau fourfold, where now the coefficients become sections of line bundles on the base, and their dependence of the corresponding line bundles is only on a subset of the divisor, depends only on the subset of the divisors, namely hyperplane divisor and in the fiber and anti-canonical divisor in the base, as well as 2 additional S7 and S9 divisors classes that I was already alluding to. So let's turn now to studying the gate symmetry in this case. Gate symmetry appears at codimension 1 singularities and is associated with the vertical divisors. One such singular locus is when S3 is 0, which degenerates to the SU2 fiber, and another degenerate locus is at S9 equals 0 that degenerates to SU3 locus. Furthermore, this construction has, in addition to the 0 section, also an additional rational section associated with the U1 divisor described by the Shioda map divisor. So we are dealing with the gate symmetry that is that of the standard model, SU3 cross SU2 cross U1. This is only gauge algebra. And if we study in more details the Shioda map, which describes the divisor associated with the U1, canonical U1 gauge field, we observe that there actually is in the whole structure, the non-trivial center of this gauge algebra, which is of order 6. We can now construct this central element whose origin is completely geometric in terms of divisors, and obtain the global gate symmetry that is now modded out by Z6 symmetry. This next step is to identify all the meta curves in the theory. Those are in the base, those will correspond to codimension 2 singularities, intersections of different gauge divisors, and they are associated with the corresponding representations. So there is a meta curve associated with this codimension 2 singularity that represents the quark doublets. Here we are dealing with lepton doublets with quark singlets, and the lepton singlet. So these representations was calculated turn out to have U1 charges that are compatible with the Z6 global constraint. We now have to do the hard work constructing G4 vertical flux to get the correct chiral index for the 3 families, and of course satisfy the D3 pole cancellations, and I will say a few more things later. But let me say, quite a long time ago, we chose the simplest choice of the base, which was P3, just the simple P3 that resulted in the first example of globally consistent model with 3 families. And and standard model gauge symmetry. So that was rather easy, and that already was indicating that there must be many more examples if we change the actual choice of the base. That leads me actually to the more recent work that led to the full landscape of standard models using really toric three-dimensional bases. So what we did then is we chose, of course, the same elliptic fibration associated with the F11 reflective polytope, which just from the fibration determines the global structure of gauge symmetry. And then we took now different bases, three-dimensional bases that are associated with 3D reflective polytopes. Of course, their structure grows. There are many more than the 2D ones. But what is crucial that with each polytope, there are many different models that are associated with different fine star regular triangulations. And basically this further data of different compactification gives us further information about intersections of different divisors. Of course, as the polytope grows in complexity, so does the triangulation. As a next step, instead of choosing arbitrary S7 and S9 divisors, we choose a special one, which is choosing them to be equal, to be in the same class as anti-canonical divisors of the base. And this is the same for all the polytopes. It's same for all the triangulations of a specific polytope. And a key thing is that if we look at the volume of the divisors associated with SU3 and SU2, they are also in the class of anti-canonical divisor, and thus they have both the same gauge group. And calculating the divisor volume of U1, which is more complicated, gives the specific answer of combination of anti-canonical divisor. And beautifully enough, these models all have gauge coupling unification. So now the hard part, we want to ensure 3 families for all this construction and cancel all the D3 tadpoles. That leads us to the construction of the G4 flux, which can be expressed in terms of products of 1,1 forums that are Poincare dual to divisor classes. This is the actually full-fledged expression for this four-form flux. And with this four-form flux, we can now go into our chirality calculation and the D3 tadpole cancellations. And what is key is that that we can express all these conditions in terms of intersection numbers of the divisors in the base. So somehow this data of associated with a G4 flux is also geometric. Now let's focus on our example that has gauge coupling unification, where these 2 divisors are the same as anti-canonical divisor. In this case, the number of families can be expressed as expected, just with the triple intersection of anti-canonical divisors. And of course, the coefficient in this combination of 4-form fluxes. So what is interesting here, if we want 3 families, we see that this coefficient actually in general is fractional, and it depends is inversely proportional to the triple intersection of anti-canonical divisors. So we are dealing with fractional coefficients there in order to ensure examples, say, with NF equal 3. Last thing now, with all this input about the chirality or number of families, we plug our G4 flux construction into tadpole cancellation and get a condition that the number of D3 branes, which has to be integer positive number, depends only on the number of families and, as expected, on triple intersection of anti-canonical divisors. So this is an expression that is the same for all the triangulations of particular polytope. So in some way, this is sort of intriguing that we get this large class of models that have certain universality properties. So geometric universality of standard model. Now, for number of 3 families, the D3 tadpole condition, namely this combination of triple intersections has to be positive integer number, can be satisfied for a finite number of triple intersections. And it turns out among them, 4 of them are in the toric class. So that allows us now to really analyze all the triangulations for all these toric polytopes. And actually, some of it is combinatorial, some of it is estimation, which led us that we are dealing with quadrillion examples of models that have gauge coupling unification and standard model gauge symmetry with 3 families of quarks and leptons. So I'm going to refer to those guys as quadrillion standard models. So this is the first part of my talk, the old summary. And now I want to really report on the progress that we are making within this context, that we want to go beyond the information on the chirality only, namely 3 families. We want to get the exact massless matter spectrum and possibly identify the domain where we would have just the exact spectrum of the minimal supersymmetric standard model. So that leads us to a more complicated issue, which is counting of matter vector pairs, which are actually the detailed counting of this matter vector pairs depends really not on G4 only, but on more detailed information on the C3 potential, which is encoded in the intermediate Jacobian of the Calabi-Yau fourfold via the linear cohomology. So this is pretty horrendous expression, but the outcome of this analysis is that when this details of the C3 potentials are restricted to the matter curves, the C3 actually defines line bundle on this matter curve, whose zero cohomology would be associated with the chiral matter in representation R of this matter curve, and first cohomology will be related to the complex conjugate representation. Let me just remind you again that on the other hand, chiral index, which is the difference of number of H0s and H1s, depends really not on C3, but only on G4 and is topological. Generically, it is anticipated that the data on matter representation in its conjugate pairs is something that is non-topological and will change as we change complex structure of the compactified space. So we would like to count this matter vector pairs for this quadrillion standard models. And really, at the end, the goal is to find the full range of complex structure moduli space of FTR compactifications, which produce precisely the MSSM matter spectrum. Well, this is in principle very hard, in part because flux is hard, and in part because the genera of these matter curves are very high. So we did some warm-up work first for a much simpler example of GATT toy model, where we constructed line bundles on the matter curves within DPF3, where matter curves were chosen as hyperplane constraints of DP3. And in this case, the line bundles on these curves were direct pullbacks of line bundles in DP3, namely much simpler analysis, but we could be very quantitative and we could analytically count jumps in number of vector pairs by employing Brill-Noether theory and also applying machine learning technique. But I don't want to talk about it, and I want to jump now to the example of how far we have gotten with the studies of the vector pairs in quadrillion standard models.
You have about 5 minutes left.
Oh, really? Okay, yeah. So let me now continue. So recall that this flux construction involved coefficient A, which was fractional number, and this leads us now actually to construction of bundles of meta curves that are the so-called root bundles, somewhat generalization of spin bundles. So let me just say with few words, how does such root bundles appear? Let me multiply this four-form flux by the triple intersection of anti-canonical divisors, since this A is proportional to that. So this means that this new flux is integer value, and this new flux induces standard line bundle. Okay. On the other hand, if we now are looking at a line bundle that is A, that is a K3 root of this A prime bundle, we would obtain in principle a root bundle that also induces a line bundle on the curve, but has the property that its K3's power is the original line bundle of G prime. So so this is basically the appearance of these root bundles. And ambitious goal would be to really find the precise root bundles that are induced from F theory C3 potentials via the linear cohomologies. But this is very hard. So what I'm going to present in the last 5 minutes is a few steps in the bottom-up analysis to identify the root bundles on the curve and really provide systematic study of all admissible root bundles with cohomologies of MSSM. So a first thing that is already there is focusing on examples with no vector quark and lepton exotics. So let me show you an example. So we are dealing now with the root bundles that are product of the one induced from C3 and spin bundle. And we see that those root bundles typically depend on some fractional power of the anticanonical divisor restricted to the curve. In some cases also Yukawa couplings. And so the whole idea is to construct such root bundles on the meta curves. Now, to construct such bundles of smooth meta curves is very difficult, especially if the genus of the curve is bigger than 2, which is our case. So we are turning to another approach. We are accessing these root bundles by studying nodal curves, the singular curves, and then employing deformation theory to access the root bundles on smooth curves. Luckily, mathematicians have studied this approach and actually developed also technology how to describe construction on root bundles on nodal curves by introducing the so-called dual diagrams, where each component of this nodal curve is associated with the bullet and each node is associated with the connected lines. Then they generalize that to weighted diagrams by blowing up these nodal curves and really constructing their own blown up curves, the root bundles themselves. So we actually have performed this procedure explicitly in our context by choosing particular, say, threefold and particular doublet meta curve, working with this procedure. And due to the lack of time, I should maybe just mention that diagrammatically such dual diagram of the meta curve of quark doublets that has gives us the information on the degrees of anticanonical divisor to the second anticanonical bundle restricted to the curve to the second power. Now with the blow up, we take this degrees of these divisors also to this nodes with the right judicial choices. And then in the blow up weighted diagram, we now see the degrees of the actually root bundle P that is in each of the components. This is now blown. Those are all the components, and we see the degrees of the root bundle R. We have to add this up. We correspondingly find the actually in detail from each component what is the total number of H0. So the total number of global sections indeed constructs for us now this root bundle with H0 equal 3. Now we use this root bundle at the nodal curve that has H0 equal 3. But this is the minimal number of H0s because the number of families is 3. So as we go to deformation to the smooth curve, we use upper semi-continuity, namely we cannot increase this number, but this is the decrease this number. And so this is exactly keeps us also after deformation to a generic curve with the root bundles that have H0 equal 3. So the same story goes for other meta curves. If you can give me just 1 minute, because this is
you're starting to take up some of the question time, but you can
yes.
Go ahead and talk for a minute.
So one thing is we also in the most recent work we also really constructed all the root bundles that are on favorable basis for F theory constructions, and actually with using some clever ideas with these weighted diagrams and some toric data to show that the number of these root bundles can be constructed on particular example, but then of a polytope space of a particular polytope, but then it's triangulation independent, which was very surprising to us at the end. But there are reasons for that. Last but not least, I have a problem. Okay, last but not least, work in progress. What to do with the Higgs curve, okay? We do find limit roots of nodal Higgs curve that have the property of having one Higgs doublets, okay? But now the issue is, can we ensure that after deformation to a smooth curve, we are not losing any sections and thus losing vector pairs? And we could see that actually as an example of being at the nodal curve, as an example of having multiple enhancement of gate symmetry and multiple components of matter curves. And going to smooth case, we are dealing effectively with brane recombination with appearance of matter that gets a Higgs vacuum expectation value. I mean, alpha gets vacuum expectation value. However, if we either don't have a doublet in the first component or anti-doublet in the second component, in this case, this brane recombination process going to a smooth case will actually not give a mass to any of these doublets, and we will not lose the sections. And so this is actually the example of a stable root limit construction with one number of Higgs doublets, and the field theory arguments after brane recombination ensures precisely appearance of H0s and H1s in each component to be such to ensure that also after we go to the continuous limit, we do maintain one Higgs doublet. So if that pans out in all mathematical details, this would be very interesting phenomenon that is very counter algebra geometric. So let me conclude. I actually, I'm sorry, my computer got stuck. Oh. So this is this. Okay, so just a few things. So I presented progress report by focusing on quadrillion standard model and how far we got with constructing the actual bundles of matter curves that produce for us from bottom-up perspective the exact MSSM spectrum. Of course, the goal is to go top-down and really see which of these root bundles that we construct is sitting there in the MSSM spectrum. There are other very difficult things in this program, like Kawa coupling calculations, some minor progress in the past. And also we want to get a possible handle on systematic analysis of other possible particle physics models. For example, we don't have manifest R parity in this construction. So we would rely on domain of moduli space in which R parity coupling would be absent, and so on. Thank you.
Okay, let's all thank Miriam for the interesting talk. And I think we only have time for one question. Let's see, I see Wati has his hand raised.
Yes, Wati.
Thanks, Miriam. Nice talk. I think this root bundle stuff is very interesting. I'd like to understand it better. I have a kind of an elementary question. Yeah, I have a kind of elementary question, I think, about your, so in the quadrillion models, you have this fractional parameter A, which is, I think, clearly very tied to these root bundles in ways I haven't quite yet fathomed. But the question I have about A is you have some necessary conditions that it must satisfy, which is that your G flux must integrate to an integer over the various surfaces that you know about. But as I understand it, that's not sufficient to prove that the A you've got there defines an integer class in homology. And I mean, this is kind of related to what the stuff that Patrick talked about the other day, where we have these matrices which are not actually unimodular. So there's kind of an open question, which is how do you determine exactly what the integer cohomology classes in H4 are? And so I guess the question is, do you have a clear way of determining which A's are actually allowed and therefore verifying that your quadrillion models all have rational values that are allowed? Or are you saying that the root bundles somehow provide some additional construction which validates these models, even if the A doesn't define a well-defined cohomology class in H4Z? Is that question clear?
Yeah, it's a complex question that is bugging us from, for last 8+ years, right? Because to find the actual correct basis, right, with properly integer quantized coefficient is unclear, right?
Right. I think this is something we've all been struggling with, and I'm just kind of trying to get what you learned about this in these different points of view.
So, and the only way, when we work with, on that in the past, the only way arguments that one could say to get this quantization condition from some first principle would be possibly only via mirror symmetry. That's what Patrick also mentioned at the end, right? That's also very hard, in concrete cases that we have, such complex cases that we have, right? This is again not attainable. So what we are doing is this poor man's approach. We are checking the consistency conditions, right? If we get integer values by integrating over all the surfaces or other consistency conditions, right? We checked as much as we could from this bottom up. Okay, but I can't guarantee it. It's a little bit of a nightmare for me, because if somebody proves this is not properly quantized, then going around with all those models can be right. This, because it's bottom up, we check all the consistency checks that we can, but we have not checked top down.
Great. No, thanks for the clear explanation. That's kind of what I was understanding. So one more question is, if A is such that G is not a well-defined integer class, is the root bundle still well-defined that you're talking about, or is there a problem with the root bundle?
No, that's the whole thing. We are using exactly those A's that are not integer, because I'm doing exactly one example and construct exactly root bundle associated with this non-integer. Those are these fractional powers, on the root bundles.
Right. So you're saying the root bundle exists even if A doesn't define a good integer cohomology class. So I mean, I guess those models might be questionable if A is not an integer cohomology class, but the root bundle construction you're saying is still a good mathematical gadget.
Perfect. Yeah.
Okay. Thanks very much, Miriam. That was very helpful.
Okay, thanks. So let's all thank Miriam again. We're kind of